2, 1, 0.
This is the record-breaking reaction. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced.
This is where they are building the largest nuclear fusion reactor in the world.
Hi friends, today we are going to see an interesting scientific topic on which a lot of research is going on across the world. It's about nuclear fusion reaction. This is one of the most important promising research areas because if this is successful commercially, this can provide limitless source of clean energy. To give you a comparison, in case of nuclear fission reaction, which is the current method to generate power at nuclear power plants, there is a lot of radioactive nuclear waste being formed. However, in case of nuclear fusion reaction, you get clean energy with very low radioactive waste which stays for short term. Another interesting fact is Sam Altman, ChatGPT creator and head of OpenAI, has expressed his views that fusion energy will be the answer to address the increasing energy needs of artificial intelligence. So, if the fusion technology will prove to be so useful, why is it still not being used in power plants to generate electricity? What are the current challenges to harness this energy source, and what are the achievements made by the researchers in this field? Before we proceed to the questions, I request you to take a moment and subscribe to my YouTube channel and share it with your friends. Now, going back to understand the answers, we will first look at what nuclear fusion is in simple terms. Nuclear fusion is the process by which the sun and the other stars are powered. Scientifically, it is the process by which two light atomic nuclei combine under extreme heat and pressure to form heavier nuclei, and in this process, massive amounts of energy is released. The isotopes of hydrogen, deuterium and tritium is most commonly used atoms because their fusion reaction is the easiest to achieve at a relatively lower temperature compared to other atoms. Deuterium and tritium react at higher temperatures of 150 million Kelvin and form plasma, and they fuse to produce neutron and helium-4. While other atoms are used, the temperatures will be much higher, in the range of 200 million to 1 billion Kelvin. So basically, when two masses combine, the third mass formed is slightly lower than the combined masses, and the difference is released as energy, which is explained by Albert Einstein's famous equation E equal to mc squared. While the technology is simple to understand at a high level, you'll be surprised to know that the global nations have mentioned it could be economically useful anywhere from early 2030s to 2050s. So why does it take at least a decade to make nuclear fusion energy useful to the world? Well, for that we need to understand the concept called as gain of energy, denoted as Q. It basically measures the output energy versus input energy of the fusion reaction. It's further classified as Q scientific and Q engineering. Q scientific only considers the input energy to the plasma and compares it to the output energy created. It doesn't include the input energy required to drive the fusion reactor. On the other hand, Q engineering is a practical measure which compares the total input energy required for the plasma and to run the fusion energy system with the output energy. So, to make nuclear fusion economically viable, it's most important that both Q scientific and Q engineering are greater than 1. Currently, we have just achieved one of the conditions, Q scientific. Researchers at Lawrence Livermore National Laboratory in California have achieved Q scientific of around 1.5 multiple times at their facility. The first time they set the record is a couple of years back on December 2022 when they supplied 2.05 megajoules of energy as input and created 3.15 megajoules of energy with energy gain of 1.5. The key point to note is that energy required to power the laser is around 300 megajoules and Q engineering is just 0.01. This means the nuclear fusion reaction must produce 100 times more energy so that Q engineering becomes at least 1 to break even. That is why even in today's scenario, nuclear fusion is not economically feasible. The amazing thing to note is that a lot of progress is being made around the world in this field. Firstly, a world record was achieved a few months back where a group of European researchers working on JET experiment have created 69 megajoules of energy from just 0.2 milligrams of fusion fuel. To give you an honest comparison, the energy released from this quantity is 10 times that of burning fossil fuel, but without any greenhouse gas emissions. Secondly, superior magnets of significantly higher strength has been developed in 2021 by MIT researchers, which would reduce the size of fusion devices used, and it will generate huge cost savings. Also, another interesting fact is 35 nations across the globe, including USA, China, and India, are part of international thermonuclear project called ITER, which aims to build one of the world's largest fusion reactors. That's it for today, guys. If you have more details to share on nuclear fusion, please comment below. And if you find this video valuable, please subscribe my YouTube channel and share it to your friends. Small actions like this will motivate me to create more such videos. I'll meet you again in next video, and until then, take care. Bye bye.